lecture series on complex analysis for undergraduate students. Today's lecture is on zeros, singularities and poles. As such, we do know 0 means for any function, if it becomes 0 at any point in a given domain, then we call that point the 0 of that function. Here we would talk about only analytic function. So, first zeros of analytic function. A 0 of an analytic function fz in a bounded domain D is a point z0 in D such that f of z0 is 0. This is the simple definition of 0. We say is 0 of order m also. So, the order of 0, if a 0 has order n, if the function its first derivative, second derivative and n minus 1th derivative at z0 are all 0. That is, a 0 has order n if fz, f dash z and so on, n minus 1th derivative of f at z is equal to z0 are all 0, but the nth derivative, that is fn z0 is not 0. Then we call the order of 0 as n. A 0 of order 1, that is called simple 0. So, a 0 of first order is called simple 0, that is where the z0 would be called simple 0 if f of z0 is 0, but f dash at z0 is not 0. Let us see some examples. Find the zeros and their order for the functions 1 plus z square, 1 minus z to the power 4 whole square and sin z. Let us do one by one. Function fz is equal to 1 plus z square. When it would become 0, so we would just equate it to 0 and solve the equation. So, we would get it that 1 plus z square is 0. This says is z square is equal to minus 1. This says is that it would be 0 at z is equal to plus or minus I. Now, if I take f dash z, that would be 2z. So, at z is equal to plus or minus I, that would be plus or minus 2i, which is not 0. So, f dash z at z is equal to plus or minus I would be plus or minus 2i, which is not 0. Hence, 0 is a simple 0. So, here plus and minus I are simple zeros of this function 1 plus z square. Now, let us come to the second function 1 minus z square, z to the power 4 whole square. If I equate it to 0, what I would get? I would get that z to the power 4 is equal to 1. This implies z square is equal to 1, or this says is why I am taking it plus 1 only, why not minus 1, because just one side I am taking it. It could be z square would be actually plus or minus 1. When z square is plus 1, we would get z is equal to plus minus 1, and when z square is minus 1, we would get z as plus or minus I. Now, let us see whether we have got that 4 points at which this function is 0. The points are 1, minus 1, I and minus I. Let us see, that is what is the order of the zeros at these points. So, find out what is f dash z. F dash z from here is 2 times 1 minus z to the power 4 into 4z cube. So, if z is equal to plus 1 or minus 1 or plus I or minus I would get it 0. That is, all these 4 zeros, f dash z is 0. Now, come to the second derivative. Second derivative from here, if we do see, it would be 24z square into 1 minus z to the power 4 minus 32 times z to the power 6. Now, the first portion of this second derivative, for z is equal to plus minus 1 or plus or minus I, this function would become, this portion will become 0, but this won't be 0 neither for 1 or minus 1 nor for I or minus I. So, second derivative is not 0 at any of these points. So, what will be the order of the zeros at these points? The order of the 0 would be 2, because what we are having is fz is 0, f dash z is 0, but f double dash z is not 0. So, we do have for this function 1 minus z to the power 4 whole square, we do have 4 zeros at 1, minus 1, I and minus I, and all these zeros are of second order. Let us come to the third one, sin z. Sin z would be 0. This says is z should be plus or minus n pi. Now, what will be the derivative of sin z? We do know it is cosine z, and at plus or minus n pi it would be cosine n pi, and minus n pi, that is also cosine n pi, and we do know that this is not 0. So, what we are having is that all these points plus minus n pi for n is equal to 1, 2, 3 and so on, this is and even for the 0, they are zeros of the function sin z, and all of them are simple 0. So, f z has simple zeros at z is equal to plus minus n pi for n is equal to 1, 2, 3 and so on. Now, let us move to the what we have got, Taylor series at 0. We do know that for any function which is analytic, or that derivatives are existing at any point and in its neighborhood, we can write the Taylor series of that function at that point. Now, if that point is a 0, then what will happen? If a function f is analytic at z naught and there is a circle of radius r about z naught, then interior to it, if f can be represented by the Taylor series, that is what we are saying is, suppose f is analytic at z naught, that means we can always find out a neighborhood in which the function would be in, the derivative would exist for all points at that neighborhood, and this interior can be, and so we say is that is in this interior if the function can be represented by the Taylor series. What is the Taylor series? You do know, f z is equal to a naught plus summation n is running from 1 to infinity a n z minus z naught to the power n for the z minus z naught less than r. We do know here that this Taylor series expansions you had already done. We do know that a naught is nothing but f of z naught, and a n's are the nth derivative of f at z naught divided by factorial n for all n 1, 2, 3 and so on. Now, if z naught is a 0 of the function f, what it says is that f of z naught would be 0, that says is a naught would be 0. Now, suppose z naught is a 0 of order m, then what I would get? I would get that f of z naught would be 0, the first derivative f dash z naught would be 0, the second derivative f double dash at z naught would be 0 until the m minus 1th derivative of at z naught would be 0. What it says is that if z naught is 0, then f of z naught is 0, if order is n, then what I would get? F of z naught 0, f of n, that is all these f of n minus 1 z naught is equal to 0, but the nth derivative of f at z naught should not be 0, that is f in z naught should not be 0. What it says is z naught, f z naught is 0 means a naught is 0, f dash z naught is 0 means a1 would be 0, and so on. I would get all a1, a2 till a n minus 1, all of them would be 0, because we are getting is here the n minus, that is n, for a n I am having is nth derivative of f at z naught, all of them would be 0, but a n would not be 0, because a n is f the nth derivative of f at z naught divided by factorial n. So, this will not be 0. What it says is now my Taylor series, because I am having first n coefficients a naught, a1, a2, a n minus 1 are all 0, my Taylor series would become now summation m is running from 1 to infinity a n plus m z minus z naught to the power m for, and a n is not 0. You see, when m is equal to 1, I would get it a1 and so on. What it says is that I could write it as z minus z naught to the power n I can take out, and then multiplied with gz. So what I could write, fz I could write as z minus z naught times to the power n times gz in the region z minus z naught is less than r. What it says is, now if I take f at z naught here, I would get it from here I would get 0, and here it will be z of z naught. Since I have written it in this manner, you see how I have started. What I would get here, an z minus z naught to the power n plus an plus 1 z minus z naught to the power n plus 1 and so on. So z minus z naught to the power n I have taken out. Then what I would get, an plus 1 z minus z naught plus an plus 2 z minus z naught square and so on, and an is not 0. So g of z naught would be an, and that is not 0. So we are actually ready to state one result. Zeros of an analytic function f are isolated, that is each of them has a neighborhood that contains no other 0. So we are saying is that the zeros of analytic functions are isolated. Isolated means is in each neighborhood I do find out there is no other 0 other than the point itself. In every neighborhood of that z naught there would be no other 0 other than that point z naught. Let us prove it. Just now what we have done, suppose if z has nth order 0 at z naught, that says this, I can write fz as z minus z naught to the power n gz in the region z minus z naught is less than r. Just now we had shown, that is if fz is analytic, and it so we can write a Taylor series expansion at the point z naught, and if it has nth order 0, then the Taylor series expansion could be written over here, where gz is also an analytic function, because what would be the gz? Gz would be an plus 1 z minus z naught to the power 1 plus an plus 2 z minus z naught to the power 2, and so that is again a power series. So that is also an analytic function. Moreover, g at z naught is not 0. Now, so g of z is analytic and g of z naught is an, which is not 0. Now, we are having a, since gz is analytic, what it says is at z naught g is also continuous. What does it say? The definition of continuity says, for every epsilon greater than 0 there does exist a delta greater than 0 such that gz minus an, because g at z naught is an, gz minus gz naught or gz minus an is less than epsilon for all z minus z naught less than delta. So I have taken a delta neighborhood, you could say, because g is analytic at analytic everywhere. So at z naught also it is analytic. Analytic means that it is continuous at z naught. So by the definition of continuity, if I take any neighborhood, delta neighborhood of z naught, the difference of gz with dz naught, that is an, would always be less than epsilon. Now choose this epsilon as an by 2, and suppose for that epsilon the delta is delta naught. What we are saying is, the definition says is for every epsilon there does exist a delta. So I am saying is I have chosen epsilon as an by 2, so the delta would be delta naught. Here is actually I should have chosen epsilon as mod of an. If an is negative, then because epsilon we want a positive quantity, so ideally it should have been mod of an. Here I am taking precaution, that is an is positive, let us say an is positive. If this is happening, then what will happen? We say from here that gz minus an, this is less than mod of an upon 2 for all z minus z naught in the less than delta naught, because corresponding to this epsilon this delta is this delta naught. Now what I want to say, that in this small neighborhood delta naught, neighborhood of z naught, gz will not be 0. Why? I am saying is that there is no z in this small neighborhood naught such that gz is 0. If gz is 0, then what will happen? From here what I would get, if gz is 0, what I would get is here this dz minus an, its absolute value would be actually absolute value of an, and that I would say is smaller than absolute value of an by 2, but this is a contradiction. An I am taking a positive value, a mod of an is a positive value, I am saying is a positive number which is less than its half of the number, that is not possible. So this is a contradiction, hence gz cannot be 0 in this neighborhood. What it says is, I have find it out, if z naught is a 0 of f, then for of order n, then I can write f z as z minus z naught to the power n into gz, and gz is not 0 in a small delta naught neighborhood. This is this particular example I have taken. Actually what we are saying is that this epsilon is arbitrary, so we could use any particular neighborhood, or we can use any other neighborhood. We are getting is that gz is not 0. Since gz is not 0, that says is that my fz will not be 0 for any other z in this delta naught neighborhood, because this would be, this term would be 0 only at z is equal to z naught. Any other point is 0 of f in the z naught neighborhood, delta naught neighborhood of z naught. That says is I should have for some other z also it is 0. For some other z it would be 0 only if gz is 0 for some other z. But what we had find it out here, that in this is small delta naught neighborhood of z naught, I am finding that gz can't be 0. Hence my f cannot take 0 value in any small neighborhood of delta naught z naught. That says is my z is isolated, z naught is isolated 0. Now come to the other term called singularities. Singularities are also known as singular point. A point z naught is called singular point of function f if f fails to be analytic at z naught but is analytic in every neighborhood of z naught. So what we are saying is that if we do have an analytic function fails to be analytic but is analytic in every neighborhood of z naught, then we are calling it as a singular point. We call it isolated singular point. A point z naught is said to be isolated if z naught is singular point and has a neighborhood throughout which f is analytic except at z naught. So we have defined a singular point where the function is analytic, it fails to analytic, that is called singular point. It is called isolated singular point if it has a neighborhood throughout which f is analytic except at z naught, then in that neighborhood we call it as isolated singular point, that is its only singular point over there. Now let us see what we are having. We would relate it with the Lorentz series. Say example, tan z has a singularities, isolated singularities at plus minus n pi plus minus 3 pi by 2 and so on. You see tan z is not defined at pi by 2 or minus pi by 2 or minus 3 pi by 2 or 3 pi by 2, but is defined everywhere else and is analytic also everywhere else. So we do have, that is if I take pi by 2 say for example, then tan z is not analytic at pi by 2, but pi by 2 is the only point at which it is not analytic. Any point in the neighborhood of pi by 2, the tan z is analytic. So it has isolated singularity at pi by 2. Similarly we can check for each of these points. Let us take one more example, tan 1 by z. Now this has non-isolated singularity at z is equal to 0. That means at z is equal to 0 what we do have, it's non-singular, but in that neighborhood also we do find out the points, because we do find out that is since tan z has singularity at you could say 2n plus 1 pi by 2. So I could always find out many points in a small neighborhood of z such that tan 1 by z is not analytic at those points, or tan 1 by z has singularities at those points in a small neighborhood of 0. So tan 1 by z has non-isolated singularity at z is equal to 0. Now 1 by z has isolated singularity at z is equal to 0. 1 by z is a function which has singularity at z is equal to 0. If I take any neighborhood of z is 0 for this function, we will find it out that the function 1 by z would be analytic in all that neighborhood of 1 by 0. So 1 by z has isolated singularity at z is equal to 0. Now let us take, these are one simple examples. Now let us take another example. F z is z plus 1 upon z square into z square plus 1. We see this is a rational function, you could say, where the numerator is a polynomial as well as the denominator is also polynomials. We see simply from here that this function will not be defined for z is equal to 0, as well as it won't be defined for z square is equal to minus 1 or z is equal to plus or minus I. So we do have 3 isolated singularities, 0, I and minus I. Whether they are singularities are alright, but whether they are isolated or not. Let us take z is equal to 0. If I take any small neighborhood of z is equal to 0, you do find it out that this function would remain analytic at all those points in the neighborhood of 0. Similarly, if you do take z is equal to plus or minus I and any neighborhood of I or minus I, this function will remain analytic in that one. That you can check by the first definition also, rather than some simple methods of checking about the singularities and isolated singularities. We will discuss later on. Now, if I take consider the function log z, then origin is non-isolated singularity for log z. Why? We do know that the log function is defined for all positive real x. Now, if I take origin and I take a neighborhood in the on the real line itself only, then for all negative points log is not defined. So log z is not analytic over there. What it says is, since every neighborhood of origin will contain some negative reals for which log z is not analytic, so origin is non-isolated singularity. That is, every neighborhood of 0 will contain some points at which the log z is not analytic. That is, it is not isolated singularity, it is non-isolated singularity. This isolated singularity has some importance, we would find out little later. If it is an isolated singularity, then as I said, we can relate it with the Lorentz series. We do know that when z naught is isolated singularity of f, there is always an r which is positive such that f is analytic in that region. Isolated singularity simply means is that in a neighborhood I could find out a neighborhood of z naught in which f is analytic throughout that neighborhood except at the point z naught. That is what we are saying is, if it is isolated singularity, I could always find out number r such that f is analytic for every z in that neighborhood. So we are saying is, because z minus z naught, the absolute value this has always to be positive, so I am writing it 0 is less than mod of z minus z naught is less than r. Let us see what this is. This is you see, you can recognize very easily, it is a disk which is not taking r. This is, you could say, a circle centered at z naught with radius r. 0 is out of this one. So we could have it is a disk. So we do know that in a disk, if the function is analytic, then the function can be represented by the Lorentz series. This you had already done the Lorentz series. What is the Lorentz series? Lorentz series is that a function f z can be written as summation of n is running from 0 to infinity n z minus z naught to the power n plus summation n is running from 1 to infinity bn upon z minus z naught to the power n for all z lying between 0 is less than z minus z naught is less than r. That is in the disk. What we are saying is, if f z is analytic, we are find it out that it can be presented by Taylor series or that power series. If it is has an isolated singularity at Z naught, then in the disk we could write it as a Lorentz series. Lorentz series has two kind of terms. One is the power series terms, another is the terms where we are having is that B upon Z minus Z naught to the power n. So, this we are having is the disk, that is this is R, and we are having is Z naught is the point where this is failed to be singular, that is this is a fails to be analytic. So, this is the singular point. So, if I do have any disk over here, in this disk we can define this as this one. Now, where this a n you had done it can be obtained by these integrals as 1 upon 2 pi I integral along this curve C. The curve C that is we are taking is that this disk. So, whenever I am taking this 0 is less than Z minus Z naught. So, wherever this point this is not necessarily that this C, this could be any C, but it has to exclude your Z naught. This can be given as 1 upon 2 pi I the integral on the closed contour C of fz upon Z minus Z naught to the power n plus 1 for n is equal to 0, 1, 2 and so on. And Bn is been given as 1 upon 2 pi I integral along this closed contour C fz upon Z minus Z naught to the power minus n plus 1. You see, for a n we are having is in the denominator Z minus Z naught to the power n plus 1, and in the b n we do have is Z minus Z naught to the power minus n plus 1 for n is equal to 1, 2 and so on. Now, this when n is equal to 1, this b1 that would be actually 1 upon 2 pi I integral fz dz. This has a special significance. This b1 is called residue also. This portion which is involving the Z minus Z naught to the power in the denominator, this is called the principal part. Now, what we have come up? We had come up with isolated singularities. We had shown that the Lorentz series, when we do have isolated singularity, we can find it out that we can write the function in the form of the function can be represented in the form of Lorentz series. In the Lorentz series we do have two parts. One is part you could say power series part, another part is that is in the denominator we do have the powers of Z minus Z naught. This second part is called the principal part of fz actually. This principal part is important. Why? This principal part is going to classify my isolated singularities, because my function f is having isolated singularity at Z naught. The kind of singularities that we would identify using this principal part. Let us see how we are going to use this principal part. We do define a pole. If principal part has only finite many terms, that is, if I do have the principal part such that b1 upon Z minus Z naught plus b2 upon Z minus Z naught square and so on, bm upon Z minus Z naught to the power m, and then bm plus 1, bm plus 2 and all those are 0. Then we say that the isolated singularity Z naught is a pole and order of that pole is m. So, what we say is that then the singular point Z naught is called the pole of f. Now, so you have got now the singularity, I have isolated singularity, I have given one more term pole. What we are calling pole if the principal part has finite many terms only. And if those bm is not 0, if bm is not 0, then we would call this pole of order m. So, m is called the order of pole at Z is equal to Z naught. So, now if my m is equal to 1, that is if I do have only single element, single term in the principal part b1 upon Z minus Z naught, then it would be called simple pole. So, if pole of first order are called simple pole. Now, if so we have come up that a finite one, then it is a pole of order m, and of course first order pole we call the simple pole. But if the principal part does has infinite many terms. But before answering that question, let us do some examples for the poles. First, if z is z square minus 2z plus 3 upon z minus 2, we have to find out the poles of this function and order of that pole. Here we see is that is this function I could rewrite as z square minus 2z upon z minus 2, that is z plus 3 upon z minus 2. What we can write f z as z plus 3 upon z minus 2. So, the principal part is 3 upon z minus 2. This has a simple pole at z is equal to 2, because the principal part contains only single term. So, it is a pole at 2, and that is a simple pole because of the first order. Let us do some more example. Sin hyperbolic z upon z to the power 4. Let us write the Maclaurin series for sin hyperbolic z. It is z plus z cube upon factorial 3 plus z to the power 5 upon factorial 5 and so on, and z to the power 4 is in the denominator, so 1 upon z to the power 4. Let us multiply it. What I would get? I would get 1 upon z cube plus 1 upon factorial 3 times z plus 5 plus z upon factorial 5 plus z cube upon factorial 3. That is, now these terms are your terms of summation a naught or summation a naught z minus z naught to the power n, and here is the principal part. So, the principal part contains 2 terms here, but you see it is not only the 2 terms. You do remember that is principal part we said is b1 upon z minus z naught plus b2 upon z minus z naught square plus b3 upon z minus z naught cube and so on. Having it here is z naught, you could see is that is we are having 0, and what we are having till z cube, that is the term b3. So, we are having actually 3 terms in our principal part where b2 is actually 0. So, we would have a pole at 0 for this function, and order of that pole would be 3. So, principal part is this one. So, z is equal to 0 is pole and its order is 3. Now, come to the question, that is, if my principal part contains infinite many terms, then we call that isolated singularity as essential singularity. So, we define the term essential singular point. If the principal part has infinite many terms, then fz has essential singular point at z naught. It is also said isolated essential singularity of f. So, for example, if I take the function exponential of 1 upon z, that is e to the power 1 by z. If I write its Maclaurin's expansion, we do know it is 1 plus 1 upon factorial 2 z square plus 1 upon factorial 3 z cube plus and so on. Of course, we will have the term 1 upon 1 plus z also. Now, you see is we will have infinite many terms in this one, that says is at z is equal to 0, it is essential singularity. So, principal part has infinite many terms. So, z is equal to 0 is an essential singularity of f. Now, we had used this Lorentz series or the principal part to define or to classify the isolated singularities. We had made it actually 3 kind of classification. One is essential singularity, another is poles, and in the poles again we have made 2 things, that is simple pole and pole of mth order. It is not only that we are just classifying this for the sake of classification. Actually, at all these 3 points, that is if the if the isolated singular point is essential or simple pole or mth order pole, the behavior of the function near that singular point changes very dramatically. So, let us see the function of the behavior of the function near poles and near this isolated this essential singularities. So, the behavior of the function at pole, let us first see it by the example. First Suppose I am taking the function 1 upon z square. If I take this one, we do know that 1 upon z square. So, this is just, you could say, is principal part, which is having the second term till second term b1 is 0, but b2 is 1, and we do have the second term. So, it would have a pole at 0 and it is of the second order. Now, how it is behaving near this 0? The function, if z is approaching to 0 from any side, now you see is that is we are not on the real line, we are on the complex plane. In the complex plane, that it says is that we are talking about the function of two variables, equivalent to the talking about the function in two variable or in the complex plane. All these things you had of course learned in the limits and all the derivatives. So, we do know that fz will approach to infinity as z approaches to 0 in any manner. What we have got, if it is a pole, then at pole it is approaching to, the function will approach to infinity from any manner z is approaching to 0. From here we do get one result. Now, I am just stating this is that if f is analytic and has a pole at z naught, then fz will approach to infinity as z approaches to 0 in any manner, that is from any direction. If z is approaching to 0, fz will always approach to infinite. You see the proof of this, how we are doing. Suppose f has a pole at z is equal to z naught of order m. What it says is that the principal part would have m terms, b1 upon z minus z naught, b2 upon z minus z square plus bm upon z minus z naught to the power m, where certainly bm should not be 0, where any of these terms could be 0, but bm should not be 0. Now, you see this portion will approach to 0 from any direction as z approaches to z naught. See, f has a pole of this one. So, what we are saying is that suppose f can be written as this manner. We do not know whatever be this a n. So, this is what we are saying, because it is z naught is a pole, that means z naught is an isolated singularity. That says in a disk 0 is less than z minus z naught is less than r. We could write f as the Lorentz series, summation n is running from 0 to infinity a m z minus z naught to the power n plus n is running from 1 to m b n upon z minus z naught to the power n, because we are assuming that is z naught is a pole of order m. This is for this one. Now, let z is z naught, that is on that disk we are talking about, and we do know that bn's and an's we are finding out as the contour integral along the simple closed contour, and that we are taking as that circle. So, let us take that circle centered at z naught as r e to the power I theta. This says is z minus z naught would be r e to the power I theta. Now, as z approaches to z naught, what I would get is that mod of z minus z naught would be actually r. So, as z approaches to z naught, mod of z minus z naught should approach to 0, that says is r should approach to 0. Now, here what we are getting is all the terms. If I write it out, I would get r e to the power I theta, r square e to the power 2 I theta, r cube e to the power 2 I m theta. Now, whatever be this theta, as r approaches to 0, for every theta these terms would approach to infinity, that is this principal part will approach to infinity. As r is approaching to 0, this principal part would be approaching to infinity for any theta. Theta means is, that is, if you do remember that we are having this kind of circle. So, what we are having is, that is either r is approaching to 0 in this direction or this direction, that is from in any manner. If r is approaching, this z is approaching to z naught, this principal part would approach to infinite, or hence fz will approach to infinity. So, this is what we are saying is, if it is a pole of any order, then fz will approach to infinite. Now, so this is happening for every pole. That now, what is the behavior of the pole at essential singularity. This is being actually done by Picard's theorem is being explained. So, let us first write this, I will just give you that Picard's theorem. Of course, we are not going to prove it, but I would show you that is how this is happening. If fz is analytic and has essential singular point at z0, it takes on every finite value in finite number of times with at most one exceptional value in each neighborhood of z0. Let us first understand what this statement is actually saying. This statement is actually telling us about the behavior of the function f near essential singularity z0. What it is saying is that if I take any neighborhood of z0, I can find out that every finite value that the function can take could be taken in finite number of times. That is, suppose f of z is say, let us say is 1, then there would be infinite many z's for which f of z would be 1 in a neighborhood of z0, and this would happen for every finite value except one value. That value, there would be one value for which this function f cannot take that value. So, that is called the exceptional value, and this is happening in each neighborhood of z0. Let us see what it is saying. Would explain this behavior through one example. The example of essential singularity for a function e to the power 1 by z we had already done. So, let us come back to the same example. We do have exponential of 1 by z, this function. We do know that z is equal to 0 is essential singularity for this function. So, now because it is essential singularity, and now we are going to use that disk that 0 is less than z is less than r. So, I would choose a z such that what we do say is that is for every finite value it will take infinite. So, now I am taking a particular point c or particular value c for fz. So, I am choosing a z such that fz, that is e to the power 1 by z, is a constant c. Since it is a constant, it has to be a complex number. We are talking in general. If it is not complex, then it would be real. So, this complex number, let us write it out as c naught e to the power I alpha t, where c naught is some constant, alpha is some constant. Now, if I represent my z by the polar coordinates rather than x and y, if rather than writing z as x plus iy, if I write in the polar coordinate, then z can be written as r times e to the power I theta. This says is 1 upon z would be 1 upon r e to the power minus I theta. We do know that by Cauchy's value, that is Euler's formula, that e to the power I theta or e to the power minus I theta I could write as cos theta minus I sin theta. So, now let us come e to the power 1 by z. E to the power 1 by z I could write as e to the power cos theta minus I sin theta upon r. Now, break it into this part, because what we want, e to the power z is constant c. So, I would like to equate, and this constant c I am writing as c naught e to the power I alpha t. So, I would try to find out what is this real part and what is this c naught and what is this e to the power I alpha t. So, from here if I do rewrite it, I would get c naught as e to the power cos theta by r and into e to the power minus I sin theta by r. So, what I would be getting is, that is first c naught I would get as e to the power cos theta by r. What it says is, from here cos theta by r would be logarithmic of c naught, or cos theta would be r times logarithmic of c naught. So, we are writing r ln c naught, and comparing it with this e to the power I alpha t, I would get it here into e to the power minus I sin theta by r. That says is my alpha would be minus sin theta by r. What it says is that sin theta would be minus r alpha. Now we do know sin square theta plus cos square theta is equal to 1. So from here if I add it up, what I would get, r square log c naught square plus r square l phi square is equal to 1. R, what we are getting is r square from here, l phi square plus log c naught whole square whole to the power minus 1, or 1 upon, that is what we are getting is r square times l phi square plus log c naught whole square is equal to 1. So r square would be 1 upon l phi square plus log c naught whole square. So I am writing it in this manner. And what will be the tan theta, that is sin theta upon cosine theta, r and r would cancel it out, I would get minus alpha upon log c naught. Now we have to find out the behavior of what we are saying is that Picard's theorem says is that this value c would be taken by infinite many jets. I have taken this one jet and I am representing that jet by the polar coordinates. So what I have to show is that for many values of r and theta I would get this c as here. Now you see here, if I choose my alpha, change my alpha to alpha plus 2n pi. Suppose I change my alpha to alpha plus 2n pi. What will happen? This c value would be e to the power 1 by z, that is c naught e to the power I alpha plus 2n pi t. So alpha plus 2n pi, I alpha is as such, I 2n pi that we do know is 1 because cos 2n pi plus I sin 2n pi and cos 2n pi is always plus 1. So this is same as c naught e to the power I alpha, that is c. So if I am changing alpha to alpha plus 2n pi, certainly this value c is not changing. Then what is happening? If I take this r, what will happen? If I am making alpha to alpha plus 2n pi, that means my r is changing. I would get this in the denominator, I would get that alpha is increasing. If denominator is increasing, then certainly my r would go to 0. We want, that is how this function will behave as this is going to 0. We are saying is that is in that neighborhood, actually I would find out infinite many points for which this is happening. Now for each n I would get a different r. What will happen to theta? Theta is minus alpha plus 2n pi. That won't change, you can check it, that is it is not going to change. So what I would get, for any jet as r approaches to 0, or as n is, the n would increase for all theta. What it says is that e to the so what we are getting is, actually let us first explain this term. For any jet as r approaches, r decreases towards to 0, r will decrease towards 0 and n will increase, and this is will happen for all theta, whatever be value of theta I do take. If I take alpha plus 2 pi, I would get one value r here, and for that actually you do see is that is for every theta, because this is now fixed up. We do get is that is for every theta I could find out a different r. That says is what we are finding it out. I could find out in polar ones, what we are saying is theta is one direction, different r's, and for one fixed r we do have different thetas. So what we are saying is for one fixed r I do have different theta on over there, and for all those theta the value of the function f z, that is c, when I am changing it to 2n pi. So let us, I am first taking the example of 2 pi. I do know that whenever I am talking about tan theta plus alpha plus 2 pi, I would be changing it towards only that making whole circle, but r value is getting changed. So for different values of n I would be getting different r's for all theta. That says there are infinite many points in that small neighborhood, such that the function is taking value, the same value c, and this c naught and this c I have taken as arbitrary. This alpha is also arbitrary. That says is that for any arbitrary finite value. The only condition is, that is, I have to take the finite, that C naught has to be finite. So, for any finite value we are getting is that there would be many j's for which f of z would be that C. Moreover, we do know e to the power 1 by z, this cannot be 0 for any z. So, in the Picard's theorem, that what they are talking about, the exceptional point, that 0 is the exceptional point here, or the exceptional value. Rather, it is not the point, it is the exceptional value. So, we do say is, that is because fz that is 0 cannot be taken for any z. So, we do have, if the function has essential singularity at any point z naught, then every neighborhood of z naught we could find out that it will take all finite values infinite many number of times, but one value which it cannot take, and that value is called the exceptional value. So, we have find it out that the behavior of a function at the isolated singularities is different according to the classification of singularity. If it is a pole, then the function will approach to 0 near the pole. If the function is if the point is not pole, then actually we are finding it out that it is not reaching to that point in any manner, rather it is having all the values in that neighborhood, it is having, but it is never reaching to that point. So, this is one example, that is what the Picard's theorem had said. So, we have got that if a point has a Picard's theorem which is telling the behavior of the function at essential singularity, we had one more result which was telling about the function of the behavior of the function at poles. So, you do find it out. Today we had learned for an analytic function what is the 0 of the function, and we had find it out that the 0 of an analytic function is always isolated, that is, it will have in a neighborhood the single 0 at that point, no other 0. Then we had find it out that if suppose a function is not analytic at any point, that point we call the singular point. We have defined isolated singular point, that says is, if in a small neighborhood I do find out that the function is analytic throughout that neighborhood except at that point z naught, we called it isolated singular point. Then this isolated singular points, we have defined that we could use the Lorentz series to define the function in a disk which is including that excluding that isolated singular point, and for that from there we had find it out that the principal part of that series, or that the function that can be used to classify those isolated singularities. That classification was necessary because the behavior of the function is changing dramatically at those points as they are classified. That is, at the poles we do find it out that the function will approach to infinite as z is approaching to that isolated singular point when the point was a pole in any manner. Then we had seen that if it is of essential singularity, it is not necessary that the function will approach to, or you may find it out that in a small neighborhood we can find out that every finite value is being taken by the function, and the function you could say you can find out infinite many points z in that small neighborhood for which that particular value would be taken. And one more thing which was crucial for that there is one exceptional value, that there may be one value in that small neighborhood, that is, in all finite values I could find out one value for which this function will never take that value. That value has been named as exceptional value of the function. So, we had learned the poles or the singularities on which the behavior of the function at those singularity points. There is one more characteristic of the singularities, but today we will not go ahead for that. We will do those things in the next lectures. So, today's that is all for all. Thank you.